this computer. All right.
Okay, so if we are restarting the in-person talks, remember we also have Zoom talks for the seminar, but today we have in person Prashanth Raman. He came from Bangalore, sorry, in India, and he's going to talk about positivity constraints in effective field theories and geometric function theory.
Thank you, Martin. I'm happy to be here and doing this in person and not on Zoom. So today I'm going to talk about certain constraints on effective field theories from positivity and geometric function theory. So this is based on work with Aninda Sinha and a few other people at IIC. Okay. So let's consider a low energy effective field theory. Let's say a linear sigma model. And the question we want to ask is, can the low energy Wilson coefficients be arbitrarily large? So we usually have some intuition about this, which we can say is a Wilsonian intuition. We say that suppose I have an operator of dimension k plus d, let's say the EFT cutoff is lambda, then we know that this operator will scale like 1 by lambda to the k, possibly suppressed by some order 1 number, but never larger. So in this talk, we are sort of going to justify why this expectation is true, sort of say what physical principle tells us that these things have to be order 1 numbers. And it turns out causality is the principle which tells you that these have to be order 1 numbers. Okay. So just a clarification here. So here by UV physics, I mean any physics that's above the cutoff. So anything above the cutoff, I'm going to be agnostic about that. But I will make certain assumptions, which I will mention in a bit. Okay, so it was realized quite some time ago that not everything goes. So these coefficients cannot be completely arbitrary. So sort of an earliest toy example was worked out by Adam, Sakani, Ahmed, and collaborators in 2006. So they considered an effective field theory of this sort, where you have a del phi to the 4 interaction, coefficient is A. And the claim is that this A has to be positive if you assume that the theory is unitary in the ultraviolet. The reasoning is as follows. So say you look at the 2 to 2 scattering amplitude. Is there a pointer?
There we go.
Yeah, thanks. Yeah, so you look at the 2 to 2 scattering amplitude. That looks like in the forward limit, that just looks like A times A squared. And I can rewrite my A as a contour integral over this amplitude by looking at this contour 1. Is write it as M4 by S cubed. I'm just speaking of the residue at that pole at the origin. Now, if I assume that my amplitude in the UV satisfies the Froissart bound, that is M4 in general, not just here, but everywhere, doesn't grow faster than S squared, as I take S to infinity for fixed t, has been set to 0. Then I can sort of deform this contour, then rewrite it in terms of the usual dispersion contour. Rewrite this guy as an integral over the discontinuity of the amplitude. Now we know that the discontinuity of the amplitude in the forward limit by optical theorem is proportional to the total cross section. So this guy is just proportional to sigma, where sigma is the total cross section. And then you can manifestly see that the integral that we get is positive because sigma is positive. Then we are integrating something positive over a positive domain. Okay, so this tells you that A has to be positive. And more generally, I mean, if you have an effective field theory where I look at coefficient of S to the n, all these coefficients have to be positive for the same reason.
So the use of unitarity is in the fact that sigma has a positive cross section.
Yeah, the optical theorem and sigma has to be positive.
So the optical theorem uses unitarity.
Right. Okay, so the point is we make a bunch of assumptions. Like I said, we are going to be agnostic about physics above the cutoff, but we make a bunch of assumptions. So we assume unitarity, and the level of unitarity here is that if I have a partial wave expansion of my amplitude, I just use partial wave unitarity which is to say that these coefficients FL, my partial line expansion, satisfy this condition, which follows from SS dagger equal 1. In fact, we are going to use only a very weak version of this. We are going to only use whatever I've highlighted in green, which is called linear.
Another naive question about the first slide. So the classical field theory is perfectly well defined for negative values of it.
Yes.
There are no issues with saddles, instabilities of any type.
That's right. So it's not something that comes just from saying the kinetic term has the wrong sign or something. It's a stronger constraint. It's not something that you would immediately have guessed.
Quantum.
Quantum.
It's a quantum constraint.
Right. So we are only going to use this weaker version of unitarity, which is called linear unitarity. We're going to assume the amplitude is local. So for instance, we assume that the amplitude satisfies the Prashanth bound. We're going to assume it's causal. So the amplitude is analytic modulo poles and branch cuts on the real axis in the S plane. And we are going to assume that there is crossing symmetry. So say we are going to look at 2 to 2 scattering amplitudes of identical particles. Okay. And the idea is just like we saw in the toy example, we want to connect UV physics to IR physics. So again, by UV physics here, I mean anything above the cutoff by a dispersion relation, and then see what these assumptions do to low energy physics. What do they say about low energy Wilson coefficients, basically? Okay. So generically, I mean, these assumptions, as you know, crossing symmetry is only proved for the case where there is a mass gap. So if the cuts join up, I mean, it's a subtle issue. There's no proof of crossing symmetry. But the second part of the talk, we are going to be talking about massless EFTs. But for this analysis, I mean, there is a way to bypass this. So what we do is, let's say I have a massless EFT, and I know that the cuts extend all the way to the origin. I haven't drawn the U channel cut, extends from there. Now, if the EFT cutoff, let's say, is lambda squared, then this big disk is where the EFT is valid. And anything below the cutoff is in principle something that I can compute in the EFT. So I can look at this modified amplitude, whatever I call M prime here, where I subtract out both the poles and this integral from 0 to lambda squared.
It's some sort of like spontaneous interacting setup that you're considering. So there is there are masses and then there are massless modes.
Yeah, in principle, I mean, there are poles. We ignore poles, right? There is a way to deal with poles also. I mean, I'm not going to be talking about that today. It's the same setup, in fact, allows you to handle poles, but I'm not going to be talking about that. But for whatever I'm going to be talking about today, I mean, this is a trick that you can do. And then you would see that M prime is something that satisfies a dispersive representation where the dispersive integral now starts at lambda squared. Okay, that clear? Yeah. Okay. And the sort of big question we are asking today is that given a 2 to 2 scattering amplitude, let's say of identical particles, which has a low energy expansion of this sort. So since it's scattering of identical particles and there's crossing symmetry, that is if I interchange ST and U, basically the amplitude remains invariant. So I can organize my low energy expansion in this form, where S squared plus T squared plus U squared and STU are the only combinations that appear. Recall that S plus T plus U is 4M squared. Okay, so these are the only two guys that appear. Now the question we want to ask is, given the assumptions that I made, what are the constraints that are implied for these WPQs? Okay, so that is the question. Okay, so there have been several approaches over the years to try to answer this question. Some have been in the 60s and 70s. They are of a very similar flavor to the toy example that we saw, where they say that certain coefficients have to be positive if you want to respect causality. But in more modern times, inspired by, let's say, the CFT bootstrap, this has been revived. And in particular, these two methods, basically, they put numerical constraints on what these WPQs can be. But crucially, I mean, all these methods they use a fixed T, what is called a fixed transfer dispersion relation or a fixed T dispersion relation. And this, as you know, breaks crossing symmetry. And what people usually do is they impose crossing symmetry as a constraint. So we are going to be using the alternate approach where we have a dispersion relation which is crossing symmetric to begin with. Okay, so here's a brief outline of the talk. So the talk has three parts. So the first part, I'm going to describe what this crossing symmetric dispersion relation is. And then by looking at the amplitude in a particular basis, we will see that, we can constrain these WPQs for the case where the external particles are massive. Okay, and here the general principles of that we are familiar with in Bootstrap. It's like positivity and rigidity and convexity play a role. So you'll see. And then we'll repeat something similar for the massless case. But the starting point is slightly different. You have to look at what is called a Mellin amplitude. Okay. The details are different, but the idea is sort of the same. Yeah, so GFT is geometric function theory.
Symmetric function.
Yeah. So I describe what
So,
it is.
just naively, can I understand this? So you're saying that most of what people do is that it's a theory of two complex variables, S and T.
Yes.
Most of the time people
Fix
fix
T
and then look at the S plane, right?
Yes.
And that breaks
Crossing symmetry.
crossing symmetry. Now you're going in this four-dimensional space, two complex dimensional space. You're going to go on a subspace that is crossing symmetry. Is that what you're going to do? Is that an interpretation of what you're going to do?
Yeah, I'm going to do something slightly different. So instead of T, I'm going to fix some other number which is complex, which involves all three variables, S, T, and U.
But the subspace you have still respects.
Yes, yes, yes.
So it's like a little bit like, okay.
Yes, exactly. Yeah, so get into the first part, which is this crossing symmetric dispersion relation. Like I said, this is what people usually consider. But since you fix T, there's no sense in which you can interchange S, T, and U because T is fixed. So this does not make crossing symmetry manifest. So to preserve crossing symmetry, first thing you have to do is you have to expand about the crossing symmetric point, because S plus T plus U is 4m squared. The crossing symmetric point is where all three of them are 4m squared by 3. So you go to these shifted variables, S1, S2, S3. And then what you hold fixed is basically this combination of S1, S2, S3, which is called A. Okay, so as you can see, A is crossing symmetric to begin with. And the dispersion relation looks like this. Okay, so this was the dispersion relation that was worked out by Overson and Khoury in 72. It was revived recently. Okay, so this,
Yeah, because like, if you go back one,
yeah.
No, and maybe you are going to talk about that, but you said yesterday that the denominator causes some problem with locality. So why do you put the denominator?
No, so yeah, at this level, we are not bothered with locality. All that we are saying is, suppose I wanted to write down a dispersion relation which is crossing symmetric. Okay, so this is the bare minimum.
S1, S2, S3. Why do you put that particular thing?
Because it has. Oh, you're saying why is A not just S1, S2, S3?
Yes, or the denominator.
Yeah, but if you fix S1, S2, S3, then for instance, you're fixing one of these combinations. Sort of the other thing is that, we also want to fix something which has dimensions of Mandelstam.
So 1 over A is 1 over S1 plus 1 over S2 plus 1 over S3.
That is 1 by A. That turns out to be 1 by A, right?
If you invert it, 1 over S1 plus 1 over S2 plus 1 over
Yes.
S3, but I'm not sure why that's better than something else.
Right. I guess the point is, I'm not saying this is a unique dispersion relation that you can write. There are possibly other things you can fix, but this is what Overson and Khoury did. So there's no claim of uniqueness here, I guess. That's what.
I guess maybe in part the question is there some sort of physical significance to this particular parameter? as opposed to all the other things with right now. Because you're gonna
Right.
fix this, right?
Yeah. Right. I guess, I mean, very naively, all that Robertson and Curry tried to do was they tried to write down something which has dimensions of Mandelstam and is fixed. So this is the sort of the simplest guy you can think of. Yeah, that's about it. There might be something to do with the parametric map, which we'll see right after this. Yeah. Okay, so the dispersion basically looks like this. So there's an absorptive part. Yes, this absorptive part is like the discontinuity that we saw in the example. There's a kernel. Kernel just looks like this, very simple kernel. So as you can see, the kernel is crossing symmetric by itself, invariant under interchange of S1, S2, S3. And the absorptive part is also something that is crossing symmetric because it depends only on my integration variable and this parameter A, which is crossing symmetric. So the whole thing is crossing symmetric. Okay, so this S2 plus, which looks slightly complicated, that just comes from this definition of A. You just eliminate S3 here. Then I have a quadratic for S2, which I can solve. And one of the roots is called S2 plus. So it turns out, because it's crossing symmetric, even if I had chosen the other root, the answer will not change. I'll just put it in this form. So this kernel, if I sort of split it into three terms, so this kernel along with this 1 by S1 prime I have, you would see that I could write it as a sum of 4 terms. So it just looks like 1 by S1 prime minus S1 plus 1 by S1 prime minus S2 plus 1 by S1 prime minus S3 and then something by S1 prime. Okay, so this is a simple algebra thing that you can do, which is basically has this advantage of reinterpreting this dispersion as an integral being done over, let's say, 3 phi cube diagrams, the 3 channels, and a contact term. Okay. So such a structure is in fact also true for string field theory, as suggested. So if you open Polchinski volume 1, chapter 6, you would find this picture for the Virasoro-Shapiro amplitude. You know that the amplitude looks like that. It has singularities in the sigma plane whenever sigma is 0, 1, or infinity. And those are these 3 colored circles. So the 0, 1, and infinity. And usually you need analytic continuation. The answer is not something that is valid for all values of ST and U. But Ashok Sen in 2019 showed how to do this without doing any analytic continuation. And basically the answer just looks like that. So as you can see, there is a number lambda here. That has something to do with the local coordinates you choose on the sphere. But you know that your answer has to be independent of this lambda. But it turns out the answer is independent of lambda only when you sum of all the 4 terms. Basically, 3 exchanges and a contact term. Okay, so that is the picture. So the contact term is basically the white circle, the white region here. Now, we have a crossing symmetric dispersion where I know that even though this guy does not have a branch cut, it has infinitely many poles on my s-axis. So my crossing symmetric dispersion also gives me a version of this answer, which is an infinite sum over all the poles. Okay, so that is what I highlighted here in red. The blue is the one which is suggested by string field theory. And then you could go ahead and compare how these guys stack up against each other numerically. So in both cases, we have infinite sums. So I could truncate the infinite sum in each case, let's say to 30 terms, 40 terms, or 50 terms. And then you could numerically compare. Okay. And there's excellent agreement. So here, just for the purpose of computing the sum, we have set lambda to 11. But as you know, the final answer is actually independent of lambda. So you could have chosen any lambda you want. Sorry for the technical slide. Is there any question?
I'm moving off here. So what was the improvement that Ashok did in 2019?
He gave a version of the answer where you do not need any analytic continuation.
No continuation and
An answer which works for all values of STN effectively. So in the original way of doing things, you know that the answer is sort of valid only in a certain region, and then there's some analytic continuation you have to do to go to certain regimes of ST and U.
but analytic continuation is unique. So that Ashok did the analytic continuation.
No, not at the level of the final answer, at the level of the representation that you get. So, for example, I know that I have something like a gamma function which is defined everywhere. I have a factorial guy, right? Let's say I have some series representation of my function. Then I know that that representation is not valid everywhere, right? There's a different series that I have to use in a different region, right? So in that sense, not in the sense of the final answer. Okay, so that was the improvement. I mean, to be able to do this without analytic continuation. Okay, so a little bit more details about how the crossing symmetric dispersion was obtained. So is this? Okay, so it's what is called a parametric crossing symmetric dispersion. So what you do is you have to parameterize my S1, S2, S3 in terms of a different set of variables. It's I and A. Sorry, it's not visible here. So what you need is you need a map between your Mandelstam and these new variables I and A, which have these three properties. What they do is, so if this is your, these are your three physical cuts, then what the map, let me show you the map. Okay, so this is what Robertson and Curry did. They came up with this map. What it does is basically maps the physical cuts in the three regions, say S3 and U, to the boundary of a unit disk. Okay, so we are going from S1, S2, S3 to Xi and A, and A is something that we hold fixed. It's a real number. Okay, so I can go from my S plane to my Xi plane. Sorry, it should have been Xi. What it basically does, what the map basically does is it basically maps these three cuts onto the boundary of this disk. Second thing it does is that it preserves low energy. So this is something that's important for us because we want to do a low energy expansion of the amplitude. So it's sort of nice that expanding around SK around 0 is the same as expanding around Xi around 0. And the third point is basically that crossing symmetry here is basically rotation by 120 degrees. If I just rotate my variable Xi by 120 degrees, I go from one channel to the other. In other words, this Xi cube is a variable which is crossing symmetry.
So is it true that Robertson and Curry did this just to get some sort of crossing symmetric set of parameters?
Yeah, crossing symmetric dispersion.
This was the motivation, and then they did this.
Yes. Okay, so in fact, these people, Mahu, Wanderers, and Roy, they wrote down a slightly different looking dispersion. It might be related to what Martin was asking, what you hold fixed. There is some degree of freedom there. Okay, so there's no claim of uniqueness, but they just found a dispersion which works. Right, so this A is something that we hold fixed, like I said. And if you want your partial wave expansion to converge, then you know that the usual partial wave expansion converges inside what is called the Martin-Lehmann ellipse. That basically fixes the range of A. If A is between minus 28 m squared and 4 m squared, that is where the partial wave expansion converges. So if you want to use this as a dispersion in the conventional sense, you want to fix A to be some number in this range. Okay. And then you do the usual thing. I mean, if you assume M is order S1 squared, as S1 goes to infinity for fixed S2, I could easily translate it to Z using my map. And then I can consider a contour inside and a contour outside. And then I can write down a dispersion relation. So that's how that dispersion relation I showed you was obtained. Okay, so this is end of part 1. Any questions? Okay. So now we're going to talk about the massive case. We're going to talk about EFTs where the 2 to 2 scattering amplitude we are considering has external particles which are massive.
Sorry, polynomial behavior, like the ratio behavior is fixed T large A.
Yes.
And here, when you have A and
Yeah,
G, what is it?
It's fixed A where you take this xi to one of the cube roots of unity. So like I said, this pink guy is the low energy regime. The high energy regime are these green points.
But the high energy with fixed T or fixed angle?
It's high energy with with fixed angle. So fixed angle scattering is you have to be around these arcs. That's where fixed angle scattering is.
Yeah, so if you have fixed T large S is ratio behavior and you know it's some S power of S.
Yes.
But half scattering is like fixed theta.
Yeah, fixed zeta. You can translate. I mean, this turns out. Sorry, this should have been zeta. Used different notation here. So that should have been zeta. So yeah, so basically fixed angle scattering is around these arcs, these red things that I've drawn here. Okay. So these points are where, for example, I fix, let's say, 2 of the 3 guys to be constants and one of the guy I'm taking to infinity. So Z1, zeta 1 here, for instance, is taking S1 to infinity, holding S2 fixed. Okay, so that's what the green points are. What is high energy? Okay. Yeah. Okay. So the object of interest is again this low energy expansion. So I could expand M in terms of S1, S2. These X and Y are sort of the crossing symmetric combinations that appear in my low energy expansion. Now I could expand my dispersion around E equal to 0, and I could compare with this low energy expansion. If I do that, I get this formula for the Wilson coefficients, Wn minus Mn. They look like. So the nice thing here is that in this formula, everything is positive except these BL and Ms. Okay, so these ALs are positive by unitarity. There's just some phase space factor which is positive. So everything in this line is positive except BL and Ms. Okay, so these BL and Ms are sort of what determine sign of terms in this expansion. Now, a key fact here is that whenever the argument is bigger than 1, all my Legenders or Gegenbauer polynomials in my partial wave expansion, they are positive. In fact, all their derivatives are positive. Okay. So in this complicated looking formula for these BLs, these PJLs are positive. So the sign is sort of completely determined by these factors. It's 3J minus M minus 2M. Okay. Doesn't matter, it's technical. If you don't understand, the point is these guys are not positive. These guys are there are negative terms in the expansion. But what you can do is you can take combinations of these guys which are positive.
Sorry, it's an infinite sum.
It's an
We're
infinite
gonna-
sum.
If some of them could be positive, some of them could be negative, there's not much you can, how do you extract some?
Yeah, exactly. So let me come to that. So first sort of trivial observation is that if you put M equal to 0, okay, then Wn minus Mn, then you would see that the answer just looks like that. Okay, so here everything is positive. So these guys are Wn zeros are manifestly positive with this analysis, and this should ring a
So
Yeah.
CLs are
CLs are Gegenbauer polynomials without any derivatives.
Right.
And this should ring a bell because this was the toy example that we saw a while ago. So these WN zeros are these GNs basically. Okay, so we have just re-derived this result in a different way. Yeah. Okay. But yeah, like you're saying, I mean, it is an infinite sum. There are sign patterns to this guy. But typically what happens is that you have some number of terms in this expansion, let's say up to some L naught, where it can be negative. Beyond L naught, they're all positive. Okay, so it's only finitely many negative terms that you have to bother about. Okay, so that is what sort of allows you to bypass. So what you can do is you can take linear combinations so that those first few negative terms you can manifestly make it positive. Okay.
Yeah.
So if you do that, you get relations of this kind.
And those were convergent sums, right? You don't need
Those
to
were
have a
convergent
combination of any type.
Yes, those are convergent sums. You just need to fix A in that range that we talked about. They're all convergent sums. Okay, so you get constraints like that. So these are what I call positivity constraints. So in fact, we know a closed form expression for all of these guys. It can be worked out. That's first thing. Second thing is that for any local theory, that is, yeah, for any local theory, basically Wn minus mm is 0 whenever n is less than m. Just another fancy way of saying that there are no negative powers of x in this low energy expansion. Okay.
Sorry, for the massless case, you have logs.
Yeah, we'll come to the massless case. Usually in the massless case, I mean, in whatever I'm going to talk about today, so we're going to only talk about weakly coupled massless EFTs where we do not include the logs. Okay. The logs can be handled, but what you need to do is you need a dispersion relation which has more subtractions. So 2 subtractions that I'm using is not enough. Okay. So using a higher subtractor dispersion relation and a regulator, you can handle logs. But I'm not going to be talking about that.
Sorry, can you give an example of that? This is a basic question, but
Yeah.
Wn zeros you said correspond to these higher derivatives del phi to higher powers that
Yes.
are coming with a friend study. So in these equations, what's W21?
Yeah, W21 is basically the coefficient of x squared y,
Lagrangian.
x squared y. So this.
Yeah, but in Lagrangian.
In the Lagrangian, I mean, yeah, they would look like some del phi to the n, and then you would have something like bunch of del squared phi.
I'm just wondering what kind of term.
Yeah.
What is exactly the constraint in the Lagrangian?
Yeah.
space?
Okay. So in the Lagrangian, I think like in the original Lagrangian that I wrote, I mean, these W's are some linear combinations of, not linear, I mean, there are some combinations of the couplings.
Yeah, but
Yeah, it's not a simple looking relation. I mean, I can't spell it out from the top of my head, but yeah. Okay, so in any local theory, these guys have to be 0. So this is a problem in our dispersion relation because we make crossing manifest. Locality is sort of lost. Okay, so just like in fixed T, crossing symmetry was not manifest and you had to impose it as a constraint. In our dispersion, basically, we have to impose locality as a constraint. Okay, and both these pictures are equivalent. Okay, this was shown in this paper. Both these pictures are the same.
Can you say a few more words about this for all again? Perhaps basic, but why is this locality constraint? What is there a simple way of saying that Wn minus mm has to be 0 when m is less than n?
Yeah, so you would have negative powers, right? So in your low energy expansion, what it means?
These are both
I have negative powers of this.
Right.
So those guys have to obviously be 0.
Sure.
That's all it's saying. Yeah. Okay, so both these pictures are exactly the same. What we gain by doing this thing is that there are some interesting analyticity properties in this variable xi, which we are going to make use of next. But let me just say a few consequences of these locality constraints. Okay, so first thing is basically spin zero partial waves do not enter these locality constraints. So in this guy, for example, even though this I've written it in a way where L starts at 0, you would see that when I put L equal to 0, this BL and M is 0. Okay, so spin zero does not enter these constraints. But if I have any other partial wave greater than 0 to be non-zero, then these couple of strong statements follow. The first thing is that I need infinitely many higher spin partial waves to be non-zero. Okay, this has to do with the fact that Wn minus M has to be 0 for all n less than m. Okay, so there are infinitely many values of n and m I could choose. For all of them to be 0, basically, I would need infinitely many partial waves to be non-zero. Okay, and it has interesting sign patterns which allow you to sort of say that all even spins up to L equal to 28 have to be present.
As you said the other day, that the first one is this Axe theorem. So
Yeah. So this is in fact an old result. I mean, Gribov, if you look at Gribov's book, Theory of Complex Angular Momenta, he does see this. And yeah, like Martin is saying, this is a version of the access theorem. But locality constraints basically tell you all this. So they make this. Okay. So what we gain by going to this crossing symmetric dispersion, like I said, is that in this Overson-Curie variable xi, the amplitude has a bunch of interesting analyticity properties. So we will sort of be interested in only two classes of analytic properties that the amplitude satisfies. So the first one is called univalent functions. So these are one-to-one complex mappings. Okay. So all functions that I'm going to be talking about are inside the unit disk. So that is a domain. And the second property is what is called typically realness. Okay. So these are functions which are real only on the real axis. Okay. And even though they are defined by a very simple definition, these actually impose constraints on the function. Okay. So which is what I mean by rigidity. So locally, if I modify the function, I also have to modify it globally. Okay. So these things translate to conditions on Taylor coefficients. Okay. So a sort of simple example to see this is if I just look at this function, z plus az squared, and I want it to be univalent inside the disk. So by definition, that just means it's one-to-one. Okay. So if I impose it, then I get an equation that looks like that. But if z1 is not equal to z2, then this tells me that this combination should not be 0 for any value of z1 and z2 inside the disk. And this can only be satisfied if this a has absolute value less than half. Okay. So just saying the function is univalent, I got a coefficient bound. So the coefficients cannot be arbitrary. Okay. So that is sort of where the power of these methods lie. Okay. These are constraining. So in fact, these functions have a connection to this particular place. So these univalent functions, there was a famous conjecture about these univalent functions, which was called the Bieberbach conjecture. It just says that if f is univalent and it has a Taylor series expansion like that, then the Taylor coefficients satisfy this relation. Okay. So this was proved by Louis de Branges, the math department here, in 1985. So this bound, it was also, I mean, part of the conjecture is also showing that this bound is saturated only by this particular function. Okay, there's no other univalent function that satisfies that bound. Okay, so that gives you the first example of what is called an extremal function. So extremal here is to be read as it saturates the extreme value.
So any Kobe function we say that between 0 to 5 is satisfied.
Yes.
So there's like a circle.
So it's like a circle of them. Okay, and these extremal functions are important for whatever we are going to say further. Okay, so let me also.
Basic question from the previous slide.
Yeah, sure.
So, shouldn't we have z1 minus z2 times 1 plus az1 minus az2 equal to 0? I don't know if it's
Yeah.
affecting the result.
Sorry, yeah, I must have made a typo. Yeah, yeah, it's probably you're right. Yeah, az1 minus az2.
Yeah, so there, I mean, I don't know, you said that it's univalent, that seems like a very strong property, so why is the amplitude is univalent?
The amplitude is not univalent. So what is univalent is basically the kernel in our dispersion relation. Okay. So univalent is sort of not what we are going to use directly. I mean, we are going to use it indirectly. Okay, so then,
I mean, from a mathematical point of view, is there some sort of a simple intuitive way of saying why these univalent functions are important? I understand they're super restricted,
yes.
but
Yeah,
they
these are
provide
just
the basis for something.
yeah, these are just one-to-one complex mapping. So if you want, say you want invertible complex mappings, of course, these are things that you need. So they're ubiquitous in that sense. If you're mapping geometric regions in the complex each other, let's say I'm going from circle to some bigly shape, and then I would also go back.
Yeah.
Then I would obviously need
Oh, I see.
some version of these guys. So they're important in that sense.
Yeah. But sort of invertible functions from
You
this
need it to be
complex.
one-to-one, of course. I mean, invertible is a stronger
Yeah.
sort of constraint. You also
Yeah.
need the inverse to be univalent.
I see.
So that's the sort of geometric intuition there. Yeah, and so the second class of important functions for us, what are called these typically real functions, they are defined like this. So imaginary part of the function times imaginary part of z is positive, except on the real axis. The imaginary part of z is 0. Okay, this is the definition. So all this is saying is that the function has positive imaginary part on the upper half plane and negative imaginary part on the lower half plane. Okay, so these were sort of introduced by mathematicians in the 30s. The first sort of application in physics was by Wigner. So he used them to, in his now famous thing called R matrix theory. So he defined these functions. So he called them R functions. Okay. Yeah. So this is also quite a strong constraint. For example, directly from the definition, a bunch of things are true. So the first thing that is true is that such a function can be real only on the real axis, can have poles only on the real axis, cannot have poles anywhere else. It can have only simple poles. You cannot have a second order pole, for example. And all these poles have negative residues. Okay. So a bunch of these things directly follow from this definition. And it has a bunch of properties which are very useful for our purposes. So 3 of them to be precise. So first one is again a coefficient bound, which I'll spell out later. Then you have these things called distortion bounds, which tell you that the absolute value of the function is sort of restricted. Okay, so this distortion bound, for example, was used by Martin in the 60s to show that 2 subtractions is enough. Okay, before a more sophisticated proof was around. And the third sort of important property that is sort of very important is what is called convexity. So directly from the definition, you can see that if I have a pair of functions f1 and f2, which are typically real, and then I take a linear combination of positive linear combination of f1 and f2, then that is also typically real. Okay, so just take imaginary part of this guy and multiply by that. You see that this is true. So it's a the space of typically real functions is a convex space.
So what does it say behind the thing?
Yeah, I don't know how to get rid of.
What does it say?
It doesn't move. Yeah, it doesn't move. I mean.
No, but what does it do? You know,
Yeah. So yeah, basically, I have a function in a domain. The point is the domain has to have parts of the real axis. So I cannot define typically real function on something that is a domain which is completely above the axis. For example, it needs to have some intersection with the real axis. Okay? Because inherently the definition involves that. I also need the function to be analytic on part of the real axis. Okay. So this is why the massless case sort of doesn't work out, because the cuts join up. Okay. So even though I have a unit disk, there's no part of the real axis on which it is analytic. Okay. So that is why massless case we will deal with in a slightly different way. But for massive case, this all works out. Yeah. So like I was saying, these typically real functions form a convex space. A nice thing about a convex space, for example, if you have in mind a very simple picture of something like a polytope, you know that you have these vertices, which are the extreme points. If you take a convex hull of these vertices, you basically get the full space. Okay. So this notion sort of generalizes to infinite dimensional spaces, and it's defined by what is called the Krein-Milman theorem. So all that it says is that I have analogs of these extreme points, which are extremal functions here. They look like that, where the zeta is a continuous parameter. And if I take a convex hull of these extremal functions, then basically I generate some arbitrary function in this space. Okay. So that is what this relation is saying.
Sorry, I have a basic question. So
Yeah.
for domain D, is there any other constraint on domain, like what should it be like?
No, there's no constraint. I mean,
Okay. And
yeah, you
it
just
doesn't have to be compact or anything. So it can be. Okay. And so you're saying containing pods, you can have intervals.
yeah, it has to have intersection with the real axis.
Okay.
Okay. And the function has to be analytic on part of the real axis.
Okay.
Then I can just define this.
Okay.
That's all it is. In fact, I mean, the version that Wigner used, he used it for the full complex plane,
Okay.
which is not compact.
Oh, right. Okay. I see. Thank you.
Okay. So without getting too technical, let's tell you what the key points are. So the first key point is that the kernel in the dispersion relation that we had is a univalent function. The second sort of important point is a fact about univalent functions. If you have a univalent functions with real coefficients, then it turns out to be typically real. Okay. So recall that our kernel is something that has real coefficients. So this is relevant there. Okay. So what both of these statements do is that they tell you that if my A is in this range, then m squared equal, I'm using small m squared equal to 1 units. So if A is in this range, then my amplitude as a function of this parameter zeta is a typically real function. Okay. So this is something you can rigorously see. Okay, so if this is true, then that helps us do a bunch of things. The first thing is we can borrow results from math, from geometric function theory of these typically real functions, and directly apply it to the amplitude. Okay, so in particular, things like the coefficient bounds that we saw, we can directly borrow, and that is what basically constrains these Wilson coefficient stuff.
So you will have to be in that regime of A.
Yeah. A is fixed in that
What,
regime.
what is that regime?
Well, it's
There are
certainly
funding constraints, but like, yeah.
Yeah, it's certainly something that is within the region where the partial wave expansion converges. The partial wave expansion, if you recall, was some -24 to 4 or something like that.
Yeah.
Certainly inside that. Yeah, at the end of the day, basically you need to be all that we want to do is you want to say something about these W's. Okay. So what range of A basically those constraints come from doesn't really matter. Like whether it's actually the forward limit or some other limit from where you
I'm
get.
asking that is it known? Is it the known limit? Is it what is this?
No,
Do we know the
this
physics of this constraint. That's all. This.
Yeah. So yeah. So basically, you just do physics of it. I don't know. So the point is, if you demand that, like I said, if you demand that it's analytic, basically I have a kernel which looks like that, right?
Yeah.
I have a denominator, so I need to demand that this doesn't have any poles inside the disk. So that basically tells me that A has to be in that range. So this zeta here is something that depends on A. I haven't spelled it out. If you actually write it out, then all that it's saying is that no poles inside the disk would give you that.
Okay.
Okay. So we can, of course, write the low energy expansion in these variables. So like I said, the answer only depends on this crossing symmetric variable, which is zeta cubed, and not individually on zeta. I have a series that looks like that, where these alpha p's are Wilson coefficients or linear combinations of Wilson coefficients. And the coefficient bounds for these typically real functions that I said I'd spell out, this looks like that. Okay, there's a bound. This kappa n is some number, doesn't matter. I mean, details are not important here.
I'm sorry, do you know what happens if you violate the bound?
Which bound?
Those,
These guys, these bounds.
yes.
Yeah, so if you violate these bounds, it means that the function is not typically real. That's all it says.
No, what, I remember some issue, if you violate one bound, it's because you have some bolts or some poles or some negative.
Yeah, so with poles, I mean, you have a different version of these coefficient bounds that I'm not going to talk about, but they're perfectly spelled out. I mean, you just get a modified version of this guy. So where these limits are different.
But in this case, when you cross the bound, you have to have some physical amplitude. Then do you know what's some physical about the amplitude or, I mean, it doesn't matter in principle, but just with the interpretation.
Yeah, it's not fully clear. I guess, I mean, some version of positivity is violated, maybe not unitary, something like that.
So
It's not very easy to see from here, actually. This level is not very easy to see.
But the argument would be you violate unitarity then.
Yes,
Both sides.
yes.
Okay.
Basically, unitarity plus the dispersion relation is what gives me this guy. So basically, the thing that I've written down here, I can recast my dispersion relation in this form. Okay. So if it is in this form, then it's typically real. Okay, there's a theorem which guarantees that. Now, the only way, I mean, you're going to violate that is to say that it's not in this form. So that means this, you cannot find a positive measure mu. That happens. So that would be violating unitarity.
So is this found, so when we were talking about the univalent functions, you mentioned this conjecture that was proved, and one of the things about the conjecture, or one of the things that you mentioned about univalent functions was that their series coefficients,
Yes.
say called Cn, nth coefficient divided by the first, or
Yes.
one has to satisfy a bound.
Yes.
Is this bound that you're finding directly related to that bound?
Yes, because these are also like I said, so these are also functions which are univalent with real coefficients.
Yeah.
So what it means is basically this kappa n is something that is bigger than minus n.
But then I was gonna say that for that case, we knew the condition for saturation of it, which
Yes.
was a unique function.
Yes.
Do you know the?
We do. Yeah, that is. It depends on which bound you want to saturate. I guess all of them you may not simultaneously saturate, but some of them, I mean, if you want to saturate, for example, this is the guy, the one that I've written down here.
Oh, I see.
That's the extremal function. For different values of zeta, you would saturate some of these coefficient
Right,
bounds.
but it sounds like you know a theory. Okay. Okay.
Yeah, there are a couple. Okay, this basically tells you there are a couple of theories. I will come to that. Okay, and like I said, so this is a convex space. So this Krein-Milman theorem tells you that once you know the extreme points, you know the whole space. So this is, for example, the characterization of the whole space. Okay. Okay, in terms of these Taylor coefficients. So you have some determinant conditions, basically.
Are these new constraints? Are they related to constraints that were found using other methods?
They seem to be new. Some of them overlap with, for example, the constraints in the EFT headroom, but some of them are new. So the nature of these constraints is slightly different. So like in everything that I'm saying, it's supposed to be true for any A in this range. Okay. So they're sort of harder to compare because I have a nonlinear constraint, which is sort of a polynomial in A.
Yeah.
So I can put A to be specific values in the domain and compare. So around A equal to 0, for example, you would see that these overlap with some of the EFT hidden constraints.
You're saying that the constraints are in different parts of this ST plane, complex ST plane. Right?
No, the constraints.
Zero, you have this A has to be in this range, which
Yeah.
cuts out the region of this complex ST plane.
No, the W's do not depend on, where they come from, right? There is constraints on W. So for example, just because I say Wn0 is positive by doing something in the forward limit, doesn't mean it's positive just there, right? These are numbers which are independent of ST.
All right, that's right.
So that is sort of where this goes. And doesn't matter where they come from. You just need a rigorous way of saying something about these W's.
Right.
Okay. Yeah, so you basically have three kinds of constraints: the positivity constraints that we saw, which we call PBC. Then you have these determinant constraints, which are nonlinear, which we call DK. And then there are these coefficient bounds, which we call TF. Okay, so these are three guys. And then what do we do using these? So first thing is that we have a result. It says that you can prove that all these WPQs are order 1 numbers. Okay. So the idea is the following. So the coefficient bounds, basically they look like that. I have a polynomial where the coefficients are WPQ and it's a polynomial in A. And basically, if you work out the ranges, you would see that absolute value of this polynomial is smaller than 3n. Okay. So I have a polynomial on this interval. Sorry. Yeah. I have a polynomial on this interval, minus 8/9 to 16/9. Which has absolute value which is smaller than 3. Okay. So this clearly implies that the coefficients cannot be arbitrary, they have to be bounded. And the point is there's an exact quantification of how large the coefficients can be. It's called Markov's brothers inequalities. You use them, you can show that any WPQ, so here by WPQ I mean, yeah, any WPQ is smaller than 5.625 in our units.
So it's P3n minus 2
Is
a
basically,
non-polynomial.
yeah, it's a known polynomial, so it's related to the alpha n's that we have here.
Why they show the formula?
Yeah. So basically these alpha p's.
Okay.
Okay, it's this time. So here, for example, you see that I have 2n plus m minus 2p. If you work out the ranges of n and m, you would see that it's a polynomial of degree 3n minus 2. Okay.
I see.
So that's the first result. So this is what justifies why these have to be order 1 numbers. Second thing is that you get regions for these coefficients, you get finite regions. So we had those determinant conditions which told us what the regions were. But if you translate it to WPQs, this is something that you can easily do on Mathematica. A linear combination of these Ws which belong to a region, I can work out where the WPQs individually lie. That gives me regions like that. Okay. So one thing that I did not say is that whatever I showed you was called the small WPQs. They're related to my Wilson coefficients in this way. So I just divide all my WPQs by W10. The W10 recall is positive. Any Wn0 is positive. So I have to do this. And the bounds that we get are called projective bounds because they are bounds on ratios of Wilson coefficients. Okay. And another thing that we can show is that it was an observation by Karen Hu and collaborators that if I look at W20 versus W01 space, the region that I get was a convex sum of these two amplitudes. Okay, so this was an empirical observation that they made. The result of their numerical bootstrap, they basically using STBB, they just empirically observed that it's just a linear combination of these two amplitudes.
But those are not known amplitudes. Those are two functions.
This is, for example, just a tree level phi cube amplitude.
Yes, that one, yes, but that's
That one is something that, yeah.
it's just a function they wrote down.
Yeah.
Okay.
So this is, yeah. So effectively what they try to do was they try to remove the spin 0 partial wave. Okay, so they just considered this guy. This is the most symmetric. These are the sort of simplest crossing symmetric amplitudes that you can write down. Okay, sum of S1, S2, S3 and product of S1, S2, S3. And then this second term comes because they wanted to sort of make sure that the spin 0 partial wave is 0. Okay, so they put the funny coefficient and did that. And what they realized is that their region was basically a convex hull of these two amplitudes. But from geometric function theory, this is sort of obvious because both of these functions turn out to be extremal. Okay, so both of these functions are proportional to the extremal function that I showed you. So region being convex hull of those guys is not surprising.
It's like a bunch of actual theories.
Yeah. So these blue things, for example, are a bunch of pion data that we have from numerical bootstrap. So there are 200 pion S matrices.
Yeah.
You can see where they lie in the region. Basically.
What is that purple?
Yeah. So
region that's
the
what's going on over there? That
yeah. So sorry, I should have said more. Yeah. The first thing is, yeah, I told you there are three kinds of constraints. I told you there is positivity constraints that we have.
Yeah.
There are coefficient bounds. So this TRU are sort of what came from the coefficient bounds.
Right.
There's the pink region, which is the bigger one.
Yeah.
And this PBC, the purple region, is basically the intersection of that region with the positivity constraints.
But then they have this region, which is some data points are outside of it.
Yeah.
What is
So
that region?
yeah. That region is basically what those guys had. Okay. In their paper. So in their paper, they sort of made an assumption where they said that even though the EFT cutoff is sort of, even though the particles are, so the mass of the external particles is sort of small compared to the EFT scale. So they set it to 0 in some sense. Okay. So if you keep m squared, you don't set it to 0, right? Then that is the sort of region you would get.
So there is pion data that contradicts that down.
It doesn't.
It's outside of
right,
that
yeah,
region.
it lies outside of that. Yeah. Because it's not strictly massless. That's the point, I guess.
Sure.
That's all. Let's see.
So suppose, yeah.
Okay. And final thing is, I mean, these nonlinear constraints are sort of hard to implement, but if you sort of, there is additional input which sort of reduces your space to either one or two dimensional guys, then in principle you could implement it on Mathematica. Okay, so a sort of game you can play is that you could consider an ansatz like this, which is what these people did. They just considered the string amplitude, the string-like looking amplitude with these coefficients are arbitrary, and they just impose what are called these monodromy constraints, which basically come from the fact that the integrand on the world sheet is permutation invariant. Okay, so you get a constraint like that. Okay, that turns out to be quite a strong constraint that fixes all my W2 and zeros to multi-zeta values. It relates most of my W's in terms of two parameters, G10 and G30. Okay, so now you have sort of reduced your problem to a two-dimensional problem. Then you could try out what these nonlinear guys are telling you, and it turns out that they give you a region they give you a very tiny island around the string solution. Okay, so this blue guy is basically the answer that you get if you impose everything, both the linear and nonlinear ones, and these intersection of these red lines is where the string solution lies. Yeah, I guess I'm over time.
We started late. How much time do you need?
10 minutes.
Yeah, sure.
Okay.
Yeah.
Okay, so massless case. So like I said, directly because the cuts join up, my typically realness cannot be rigorously justified. So here we sort of take a different way of doing this. So the object that we consider is what is called a celestial amplitude. Okay, so quick crash course on this is the key point here is basically the isomorphism of these two groups, SO3,1 and PSL2C. So this guy is basically the Lorentz group in 4 dimensions, and this is the global conformal group in 2D. So the fact that such isomorphism exists suggests that it might be possible for you to write down S matrix elements in a basis where 2D conformal symmetry is manifest. And it turns out this can be done. So what you have to do is you have to parameterize. So we are considering 2-2 scattering where external particles are massless. Okay, so that's where we are. So you can parameterize null momenta in this way. And then you do what is called, you go to a basis which is called the boost basis. So one particle states, which the momenta are now labeled by omega z and z bar. Okay. And you make a transformation, you go to what is called a boost basis, and then you define this object. Okay. This object transforms like a 2D correlator. That's the point of doing this exercise. Okay. Sorry if that is quick, but basically the point is written in this form. Mn transforms like a correlation function of quasi-primaries in a 2D CFT, where the weights h and h bar are related to this boost weight delta. Here sigma is the helicity. Okay, so h and h bar are related to delta and the helicity. Okay, so this is the object you are going to be working with. Okay. Is that clear?
Okay, maybe we can discuss.
Yeah, no, yeah, like I said, I mean, you just want to rewrite my amplitude in a way which makes it look like a 2D correlator. Then what you have to do is you have to parameterize momenta and null momenta in this way. Okay, so in this, you parameterize null momenta in that way, and then you go to this funny looking basis. Okay, so one particle states. So I'm sort of doing an integral transform. I'm doing a Mellin transform of my one particle guy. Then in fact, I can show that, for example, this state transforms like a quasi-primary in 2D with weights h and h bar. Okay, this Lorentz transformation properties of one particle states, let's say in chapter 1 of Weinberg, you just use them. You would see that this delta z z bar sigma transforms like a primary. So that motivates me to define this object. There's an integral transform of my momentum space amplitude. Okay. And basically that object looks like a 2D correlator. That's all this is. In particular, what this is telling you is that this is giving you a prescription. So given a 2 to 2 scattering amplitude, let's say for ST, what I do is I use this funny transformation. S is omega squared, T is minus Z omega squared, U is minus 1 minus Z omega squared, which basically comes from the way I parameterize my null momenta, and I just do this integral transform. Okay, this m tilde is the object we are going to be working with. Here Z and Z bar were the cross ratios. That wasn't clear. Okay, so nice thing happens if you work with this m tilde. First nice thing that happens is that you see a novel positivity. Okay, so first a definition. So a polynomial on an interval AB is positive if it is totally positive on the interval. Okay, like the name suggests. Now there's a characterization of these polynomials, which is to say that I can write them down as a positive linear combination of positive things on the interval. Okay, so 1 plus x and 1 minus x are things, for example, 1 minus 1 1, which are positive. Now I can write down p in a way like that, where ci's are all positive. Okay, so that's a characterization of such positive polynomials. Okay, so if I can write down a polynomial in this way, then it's a positive polynomial on the interval. Okay, here's an example. Now, what I do is basically I go to this variable rho, which is a crossing symmetric variable. As you can see, because rho is proportional to, or it involves, it's a combination of z and 1 minus z. And interchanging z and 1 minus z is basically interchanging t and u. So I go to this variable rho. So my usual x and y look like this in rho. Okay. And if you look at your favorite amplitudes in this basis, then you see the following. So you see that they are all positive polynomials basically. So this is closed bosonic string amplitude. This is type 2 amplitude after I subtract out the pole. This is tree level phi squared psi. This is 1 low phi squared psi, where phi is massless and psi is massive. Okay. So you look at all of them are positive. Okay. So this is what we call novel positivity. Sort of big question is what explains this positivity. Okay, that's first thing. Second thing is I can compute this object m tilde beta z given any momentum space amplitude. One such momentum space amplitude is my crossing symmetric dispersion relation. So I can just plug it in and compute. Okay. So if I do that, I get this complicated looking answer that these alpha tilde j's are moments. I mean, alpha tilde j's are this integral of my partial wave moments. So first thing is that all the information about dynamical information about my theory is in these alpha tilde j's. Everything else is universal. And these blue terms basically are like what we saw in the crossing symmetric dispersion relation. They correspond to 3 channels and a contact term. And this green guy basically tells me that in this basis, we have poles whenever beta is an even integer. So what Arkani, Ahmed, Strominger, and a few other people proposed is that basically if I look at residues at beta equal to -2n, then that has information about IR physics. And if I look at residues at beta equal to +2n, then that has information about UV physics. Okay. So since we are interested in low energy physics, we're going to look at residues at beta equal to -2n. So that is the object of interest. Okay. So this object, if you compute, I mean, from the expression that I just showed you here. So this has possible singularities in my rho plane. So 2 possible locations of singularities are at rho equal to -1 and rho equal to +1. Okay. So it turns out the rho equal to -1 singularities aren't actually there. So what happens is if I sum over all my 3 terms, basically they cancel. They're not really there. But the singularities at rho equal to +1 are there. And demanding that they are absent is what leads to locality constraints in this basis. Okay. And we can, in fact, compute this object using a math result. We'll not get into that. But the key point is the locality constraints have a structure that looks like this. Okay. So if I compute the residue, then basically I have 2 terms. One term is a polynomial in rho. There are no poles at rho equal to 1, and then there's a piece which explicitly has higher order poles in rho at rho equal to 1, and those have to vanish. So that is locality. Okay. And if I write it out, the locality constraints look pretty nice. So the alpha tilde j's, because I put beta equal to -2n now, these are partial wave moments. Okay. So what this is telling me is that an infinite combination of partial wave moments is 0. So this is something that every local theory has to satisfy. Second thing is that the sum starts only at j equal to 2. Spin 0 does not enter this whole analysis. And similar things to whatever we saw for the massive case hold true. You need infinitely many of them to be non-zero, which is a version of the Sachs theorem. Like. And the nice thing is, I mean, if I do it for different values of n, I get bounds which look like that on the partial wave moments. So things like spin 2 partial wave moment by spin 4 partial wave moment has to be bigger than a certain number. So this is what is called low spin dominance. This is something that people have observed in low energy massless EFTs. And the claim is that this low spin dominance is a consequence of locality. That's the first result. Second result is that spin 0 dominance is what actually gives you rho positivity. Okay. So I'll not get into the details, but that is sort of the result. Spin 0 dominance is what gives you rho positivity. And third thing is that once you impose locality, basically once you pretend these guys are 0, then I told you that you have a piece which is polynomial in rho. So those are what are called Feynman blocks. And those Feynman blocks basically they give you an alternate basis to do your expansion in. So instead of partial waves, I can expand, for example, any amplitude in these Feynman block basis. The convergence in J is fast. They have nice sign patterns. Okay, so I've listed the first few Feynman blocks here. Nice thing that happens is that these Feynman blocks, it turns out, are typically real polynomials beyond a certain value of J. Okay, so that is where all of this is going. And the extreme points of these typically real polynomials were also classified as if theorem tells you what they are. Okay. So for example, if n equal to 2, then the space of these functions is a line. If n equal to 3, the space of these functions is that curve. And then you can use similar techniques and you get bounds in W's. Okay, so these are by nature non-projective. Here we do not take ratios of Wilson coefficients. That's what it is. So that's it. I stop.
Other questions? We had a lot of questions during the talk. So if there are no more questions, let's thank you. Thank you so much.
Yeah, sorry, I went way over time.
No, it's all right. Stop. I think we start late as well. It's just